Hey everyone, welcome back. Today, we are tackling a massive and honestly super exciting topic in our C programming journey. We're diving into Chapter 7, all about arrays. Now, because C gives you so much incredible control over your computer's memory, we absolutely cannot talk about arrays without having a rock-solid understanding of memory addresses. So to make sure we're totally ready, we're going to kick things off with a quick recap of Chapter 6 on pointers before we unlock the real power of arrays. Here is our game plan for today's explainer. We'll start with that quick pointer recap, officially introduce arrays, see how they actually look in memory, cover some pointer arithmetic, figure out how to pass arrays to functions, and finally wrap up with multi-dimensional arrays. Let's get right into it. Section 1. Recapping C pointers. Let's anchor ourselves and review the absolute basics from our last chapter so we're set up for success. Okay, so whenever we write a C program, every single variable we declare has to live somewhere inside the computer's memory. Take variable I, for example. It holds the value of 72, right? But underneath that, I lives at a very specific memory address. In this case, it's 87994. Now, a pointer is simply a special type of variable that stores the memory address of another variable. Look at J. Notice how J doesn't hold a standard number? It actually holds that address, 87994. To make this happen, we use the ampersand operator, which is the address of operator, to find exactly where I lives. And then we use the asterisk operator, the value at address operator, to peek inside that address and see the data. Pointers are basically your VIP pass to directly manipulate memory. I really want you to keep that mental image of memory addresses locked in your mind for this next part. Because now that we know how pointers work, let's learn about arrays, another fundamental concept in C. Section 2. Introducing C arrays. Before we get into the syntax and the how, let's talk about the why. Why do we even need arrays in the first place? Well, imagine you're writing a program to store the grades of 90 different students. Without arrays, you'd be forced to declare 90 individual variables. You'd be typing out marks 1, marks 2, marks 3, all the way down to 90. I mean, that is literally a coding nightmare. Arrays fix this problem beautifully. An array is just a collection of similar elements that allows a single variable to store multiple values. So instead of 90 separate variables scattered all over your computer's memory, you get one neat, organized collection. Declaring an array in your code is super simple and takes just 3 steps. First up, the data type. Every item in an array has to be the exact same type, like int for integers. Second, you give it a name, something descriptive, like marks. Third, and this is where the magic happens, you use square brackets to set the size. By just writing int marks 90, you're telling the C compiler to instantly carve out space for 90 integers under one single name. You can do the exact same thing for characters to make strings or for decimals using float. And that brings us to the absolute golden rule of C programming. Look closely at the index numbers underneath the boxes here. Notice anything? They do not start at 1. They start at 0. The very first element is accessed using index 0, the second one is index 1, and so on. Honestly, forgetting the 0 indexing rule is the #1 cause of bugs when you're starting out. So please, burn this rule into your brain right now. You can also set up the values inside your array at the exact same moment you declare it. If we write int CGPA 3 equals, and then open curly braces, 988, close curly braces, we're declaring an integer array named CGPA with a size of 3 and immediately filling index 0 with 9, index 1 with 8, and index 2 with 8. It's really that clean. By the way, if you have any questions or doubts about this setup, just leave them in the comments. Your question might be answered in a future explainer. Section 3. Arrays in memory. Now let's connect everything we've just learned about arrays right back to our pointer recap. What is actually happening physically inside your computer's RAM when an array is created? Let's look under the hood. When we declare an array of 3 integers, the compiler knows a standard integer takes up 4 bytes. So it goes to your RAM and reserves a perfect, uninterrupted, contiguous block of 12 bytes total. Trace these memory addresses with me for a second. The first box starts right at address 62302. The second box starts exactly 4 bytes later at 62306, and the third is at 62310. Arrays are absolutely guaranteed to be stored right next to each other in memory, kind of like a row of connected townhouses. Section 4. Pointer arithmetic. Because arrays are perfectly spaced out contiguous blocks of memory, we can use pointers to effortlessly navigate through them. This unlocks a massive concept known as pointer arithmetic. Now, normal math doesn't quite work the same way with pointers. If you have an integer pointer holding the address 87994, adding 1 to it doesn't just make it 87995. Because integers take up 4 bytes, adding 1 actually tells the pointer to jump 4 bytes forward to the very next integer, landing squarely on 87998. C allows 4 main operations here. You can add a number to a pointer, subtract a number, subtract one pointer from another to find out how far apart they are, and compare 2 pointers together. And here is where things get really cool. In C, the actual name of the array itself essentially acts as a pointer to its first element. Literally, if you have an array named R, just using the word R by itself gives you the memory address of index 0. This is proof that arrays and pointers are just deeply, fundamentally connected to each other. Let's trace this little block of code line by line to see it in action. On line 1, we create a pointer named PTR and give it the exact address of the array at index 0. Then on line 2, PTR++, we increment that pointer. Because it's an integer pointer, it smoothly jumps exactly 4 bytes forward, landing us perfectly on the address for index 1. Finally, on line 3, we use that value at address asterisk operator to reach in and pull out whatever value is stored at index 1. This is exactly how we can walk through an entire array using pure memory addresses. Section 5. Passing arrays to functions. Knowing that an array name is really just a disguised pointer completely changes the game when it comes to sharing arrays with other parts of our program. Take a look at these 2 different ways to write a function prototype that accepts an array. Over on the left, we're telling the function to expect an integer pointer, but on the right, we're telling it to expect an array using square brackets. Here's the secret. To the C compiler, these are effectively the exact same thing. When you pass an array to a function, you are absolutely not copying over a massive, heavy block of data. You are simply handing over the memory address of the very first element. It's incredibly fast and incredibly efficient. Section 6. Multi-dimensional arrays. Up until now, we've mastered the standard flat, single-line array. But data isn't always a single line. Sometimes we need grids, matrices, and tables. Let's expand our horizons. Instead of just one set of square brackets, we just use 2. Declaring int r32 creates a 2-dimensional array. Just think of it as 3 rows and 2 columns. Notice how we initialize this thing. It is literally an array made up of other arrays. We have our main outer curly braces, and inside 3 inner arrays. To grab the number 9, you just ask for row index 1, column index 1. But wait, let's stop and think about the hardware for a second. Your computer's RAM is not actually a 2D grid. It's just one super long, flat line of memory addresses. So how does C pull this off? Simple. It flattens it out. It places the first row into contiguous memory, then immediately follows it with the second row, and then the third. The grid is just an illusion maintained by the compiler's math. Underneath it all, it is still just one beautifully, perfectly contiguous block of memory. Honestly, the absolute best way to truly grasp arrays is to just write the code yourself. So here are your core practice challenges for Chapter 7. First, try creating an array of 10 integers and storing a multiplication table in it. Next, write a function that actually reverses the elements. Then, try counting the positive numbers in an array. And for a real challenge, take user input to fill up a 2-dimensional array and print it out as a nice, clean grid. All right, let's do a rapid-fire recap of our 5 key takeaways today. 1. Pointers hold memory addresses. 2. Arrays collect similar elements all under one name. 3. Arrays use zero-based indexing. Never forget that. 4. Arrays are always stored in perfectly contiguous blocks of memory. And 5. The name of an array acts as a base pointer to its very first element. If you're enjoying the C programming series, don't forget to like this explainer and subscribe for upcoming chapters. Before we go, I want to leave you with a bit of a provocative thought. We've seen today that C basically trusts you completely. It lets you use pointer arithmetic to jump smoothly from index 0 to 1 to 2. But what if you tell your pointer to jump to index 100 in an array that only has 3 elements? C doesn't natively protect you from yourself here. So what kind of absolute chaos happens to the rest of your computer's memory if you step out of bounds? Think on that memory safety risk, and we will explore the wild consequences in Chapter 8. Happy coding!